Hello, everyone. Welcome to my presentation. My topic today is related to operating system kernel, memory access, mapping, parsing, and risk condition issues. The title is Diving into Kernel Memory Mapping and TOCTTOU Vulnerability. My name is Wang Yu from DD Research America. I can be reached through this email address. This research is the third kernel security research project I made public in 2020. The first two projects are related to the Bluetooth and Wi-Fi subsystem of macOS and iOS. Today we have 4 parts: background, Project Kimon, kernel vulnerability case studies, and the end. In the first part of the presentation, we will focus on the background knowledge of user mode memory access and the kernel risk condition vulnerability. Let's start today's journey. When developing operating system kernels and drivers, functions related to user data mapping, accessing, and parsing are often found vulnerable. In order to solve this type of problem, almost every system defines standard operating rules when touching untrusted user input. In this section, I will list the user mode memory access method of Android Linux, Windows, and macOS iOS platforms, as well as some real-world vulnerability cases. The first platform is Android Linux. In my opinion, the Linux kernel API document is worth reading. The first chapter of the document is named Memory Management in Linux, in which user space memory access describes in detail the API set that should be used when accessing untrusted memory. For example, the well-known functions copy from user and copy to user. Their explanation can be found in the links below. If their rules are violated when accessing user data, the vulnerable function will at least introduce a local privilege escalation vulnerability into the kernel. The simplest but real case is as follows. I discovered this vulnerability when I was working on mobile security research 7 years ago. We can still find the leaked source code on GitHub. The vulnerability is located in the MediaTek SD card driver. Due to lack of restrictions, user mode processors can open and operate this driver. Through auditing the leaked source code, we can find that almost every I/O control handler of the driver has problems. For example, in line 994, the function copy from user mistakenly trusted the length of the input. The size of the buffer on the local stack is only 25 bytes, and such a copy means that stack-based buffer overflow. In general, this vulnerability gives you a chance to be guarded. Of course, all of this is based on the fact that 7 years ago, there was basically no mitigation mechanism for mobile phones. But this simple exploit took me a lot of time. At first, I found that no matter what I tried, I could only get my phone restarted. So I had to re-examine the last return instruction of the vulnerable function. Without the help of kernel debugger, I guessed one by one about the possibility of overwriting the registers. Destroying the blue register like R4 or R5 may cause the caller function to crash, because the value in this register may be a base address of an object, and we cannot just override it. Destroying the green PC register means that we need to figure out where to put the shellcode. The good news is that security features such as PXN were basically not enabled on mobile phones in 2014. With the deepening of the analysis, I found that the red SP register is a key to the problem. I broke the SP address before handling the return address. So why? Why the SP register so critical? The answer is related to current thread. In order to improve the speed, each operating system uses the simplest method to locate the current thread structure. For example, the Windows kernel determines current thread based on the fixed offset of the FS register, while in the Linux kernel, like version 2.6, current thread is located with the help of SP register. Therefore, once the Stack Overflow corrupts the SP register, it will cause serious problems during context switching. That's why I have to turn off interrupts in the shellcode first. The next question is, where we should return to after the shellcode is executed? The problem is not difficult for us, I think. We need to search the code segment, find the return address of the BL instruction, and then redirect the execution flow of the exploit to that location. In this way, our code can be executed stably. The following figure shows the complete process of vulnerability exploitation. First of all, we need to select the appropriate value of R4, R5, and other registers, and select the appropriate address to place shellcode. Once the shellcode is executed, we need to turn off system interrupts at the first time, and then search the double-linked process list to find our own task structure. By locating the correct SP offset through, for example, signature search, we can restore the SP register. Then we can re-enable the interruption and complete the process of escalation. In the last step, we need to search for the correct return address and exit. By the way, we don't have kernel debugger, and we cannot print out debugging information because this will cause context switching. So this page contains a 7-year-old screenshot of a successful EOP, privilege of escalation. To avoid trouble, I removed the name of mobile phone brand. The vulnerability is actually caused by the vendor's SD card driver. This vulnerability affected many mobile phone brands at that time, including Samsung, Xiaomi, Huawei, and so on. In the third part of this presentation, we will see other vulnerability cases caused by graphics card supplier. As a summary of Android Linux part, I want to make a few points. Number one, all input is harmful or potentially harmful. For the vulnerability mentioned earlier, I think every kernel programmer should try his or her best to avoid making such mistakes. Number 2, stack-based buffer overflow exploitation in the real world is not as simple as in books, especially when you don't have a kernel debugger. And number 3, you may be wondering, do Stack Overflow vulnerabilities still make sense today? For this question, I want to give 2 examples. The first one comes from the presentation of Pangu team, Wang Tielei, at Black Hat USA in 2019. The title is Towards Discovering Remote Code Execution Vulnerabilities in Apple FaceTime. On page 101 of the slides, Tielei discovered some cases of Stack Overflow caused by the compiler's incorrect insertion of stack canary on ARM platform. The second example comes from my presentation at Black Hat USA last year. Diving into Apple I/O 8.02.11 family version 2. I found a case where the compiler did not insert the stack canary for the target vulnerable function. The ID is CVE 2020-9899. I think after reading these presentations, you may have some different ideas about stack-based buffer overflow. The next platform is the Windows kernel. I would like to share some more interesting cases with you. First of all, this is slides called Common Coding Errors that is worth reading. It contains most of the common kernel programming errors and solutions. As part of the user mode data processing rules, routines such as prop4 read and prop4 write are APIs that we must use. Their explanation can be found in the links below. Similarly, if the rules are violated when accessing user data, the vulnerable function will at least introduce a local privilege escalation vulnerability into the kernel, Windows kernel. In 2012, I mentioned an interesting feature in the Win32k font engine in my font security related presentation at the Syscan 316 conference. For efficiency reasons, font files will not be copied into kernel mode. So how does the kernel scalar engine access this data located in the user space? The answer is the engine will access and manipulate this data directly. In the figure, we can see that the return value of the routing pvGetPointer callback is a user mode address with a length of 4E8 in hex. And all subsequent parsing operations are based on this user mode address. In my opinion, this design and implementation gives TOCTTOU or risk condition vulnerability a large living space. By the way, TOCTTOU is short for time of check to time of use. It's a kind of risk condition vulnerability. A year later, Juro from Google Project Zero released his BoxPawn on GitHub. This amazing tool found a large number of kernel double fetch and risk condition vulnerabilities. Some of these records can still be found on Google Docs today. BoxPawn can record all access actions of the kernel to user mode data. And vulnerabilities types like double fetch will have nowhere to hide. Then Jura turned his research direction to the Win32K font engine. And again, his tool found a large number of double fetch and TOCTTOU vulnerabilities. I listed some of his blog here. If you are interested in font security, these blogs should not be missed. These excellent studies keep me thinking, what else can I do? In general, there are only two ways left. The first way is to improve the code coverage rate during vulnerability hunting, and maybe I can find some missed cases. The other way is that I must try to find some new vulnerability patterns. I shared my approach in the Black Hat USA 2014, and my slides can be downloaded in the first link. In short, I mainly did two things. I compiled the font scaler engine in the kernel of leaked Windows NT source code. Yes, it can be compiled, and it is possible. I compiled all project codes into a static library in user mode. And then I wrote a corresponding application to drive it to work. And I uploaded the project on GitHub here. Because I recompiled and repackaged the source code, my slides should not be put on the official website of Black Hat. But I think the whole process is very interesting. For example, on the left, I can get all the symbols of the font engine. I can also see how each glyph rendered in pixel. This is a Windows logo and how it works. The second thing is that I did find a new type of vulnerability. Its ID is CVE 2014 1819. Because of the font engine introduced a caching mechanism in Windows XP, I found that the logical of many kernel routings has become first, go to query the font cache. We can call it the first fetch. Then the kernel buffer is allocated according to the size of the first query. Next, access the user mode data to initialize the kernel buffer, which we can call the second fetch here. As you can imagine, there is a huge time window. Any inconsistency between the first fetch and the second fetch will result in heap out-of-bound access. This vulnerability pattern can perfectly avoid BoxPawn scanning because there is only one user mode data read or fetching in the entire process. As a summary, I want to say again that all inputs is harmful, and new features or new changes always mean new attack surfaces. The font cache introduces new TOCTTOU vulnerabilities to the kernel, and this non-traditional double fetch vulnerability are very difficult to capture. The third platform is the macOS and the iOS kernel. On macOS and iOS platform, the situation becomes a little more complicated. Functions like IO_connect method can automatically handle user input for the kernel and the extensions, while BSD functions such as copy in and copy out provide support for manual operations. In the link above is a document called Kernel Programming Guide. Although some of the content in the document is out of date, but I still recommend kernel developers to read it as a reference. For the more commonly used IO-kate functions, I have listed some links such as IO connect call method. Inside the IO connect call method function, many code branches are related to the class IO memory descriptor. So I also list the IO memory descriptor documentation below. Next, I want to refer a blog post by another speaker today, Flanker. This 4 years old blog explains in detail a vulnerability pattern related to memory mapping in the macOS and iOS kernel. The ID of the vulnerabilities include CVE 2016, 7620, 24, and 25. Regarding the topic of memory-related vulnerabilities, Ian Beale has a blog in 2019 that I have to mention. If you are interested, this article is also worth reading. Today, due to the limited time, I have to limit the discussion to the first Flank's blog. For friends who have not read this blog, I will use the simplest words to summarize the root cause of the TOCTTOU vulnerabilities. Inside the IO connect call method function, the user mode input will be processed. If the input user data size is less than 1 page, this function will use the memory copy method to copy all the data into the kernel. On Linux platform, we call it copy from user. And on Windows platform, this operation is named probe and capture. So the problem is that if the input data is larger than 1 page, IO connect call method will create a memory descriptor to describe the target data. And at this time, the user process still has write permissions to the mapped data. So let's think about it. What does write permission mean here? It means TOCTTOU attack. So in this blog, Flank also gives Apple's fixed solution, which seems to be related to the VM copy flag. If you are interested, you can read the then source code on GitHub. The link is here. As a summary of this section and the first part, I want to say penny, penny, penny. All inputs are potentially harmful. One more thing is that does the security update really work? To me, this is a very good question. I mean, this security update, does this really work? Okay, the next section. After seeing this, you might say that the cases are not the latest vulnerability. They are just some end days, not 1 day, not 0-day vulnerability. I would say if we want to find more interesting vulnerabilities, we must have powerful tools in hand. Here, I want to introduce Kmon to you. In this chapter, I will explain what Kmon is and what problem it can solve. Kmon is an open source pre- and post callback-based framework for macOS kernel monitoring. Its source code can be found on GitHub, dd/Kmon. KMON includes many useful features, including file, process, network traffic monitoring, dynamic library and kernel extension monitoring and blocking, mandatory access control policy filtering, and so on. In addition, KMON also integrates a kernel inline hook engine, through which we can hook almost any kernel function we want. And some of the above functions are not that easy to implement. For example, for file and process operation monitoring, KMON's solution is based on the kiosk KPIs. KPI is short for kernel APIs. But the kiosk has many limitations. For file opening, the kiosk callback cannot distinguish whether the operation is create new or open existing. For process creation, the kiosk callback cannot get the command line parameters. This is unacceptable for kernel monitoring. There's no context. But all of this can be easily solved. This screenshot is to locate the command line information by searching call stacks. Yeah, here. Another interesting topic is related to macOS mandatory access control policy. The security implementation of macOS and iOS almost all relies on the MAC mechanism. So is it possible for us to dump the kernel mandatory access control list? Yes, it is possible. But a potential question of this requirement is how to obtain unexported logs and access kernel data structure safely. Such challenges cannot stop us. After reading the kernel source code, I found that there were two callbacks opportunities for the third-party extension between the code that obtained the mutex log. This means that I can safely access and dump mandatory access control related data structures in the callback functions. And here is a demo. I can filter in policy registration. For the kernel inline hook engine, it will insert pre and post callback handler for the target function. In the pre-callback handler, we can filter the input parameters. And in the post-callback handler, we can modify the return value of the function. This screenshot is an application of the KMON kernel inline hook engine. I hooked up functions related to kernel extension loading and unloading. As you can see that I passed and filtered the input parameters of the function in the pre-callback handler. I can even patch the target kernel extension to block it to be loaded into kernel. With the powerful support of KMON, I built some sniffers and fuzzing tools. This year, I published 2 research projects. One related to Bluetooth security and the other related to Wi-Fi security. They were presented at Black Hat USA and Black Hat Europe conferences. This is a request sniffer for IO802.11 family. Get and set request. We can see that the kernel receives a large amount of user data from the daemons such as airport D. And like this one, the length is 930 in hex. some of the request data contains complex formats. And I have reported about 18 vulnerabilities to Apple, some of which have been fixed. And this one is a sniffer for I/O Bluetooth family HCI requests. HCI is short for host controller interface. We can also see that the kernel receives a large amount of user data from daemons BluetoothD. More complicated is that third parties can customize their own vendor-specific commands. And almost all these vendor-specific commands are not documented. Here, you can see FD, 4C, 4B, 4A, 4D. They are all belongs to Broadcom vendor-specific command. And I have reported about 23 kernel vulnerabilities this year, some of which have been fixed. With the help of Kernel, I hooked up almost all kernel mapping related functions. This engineering practice have given me a better understanding of the implementation of kernel mapping. And these sniffers can be easily transformed into fuzzing tools. For example, I can do bit flipping very easy. In addition, this year I also implemented a simple kernel address sanitizer. It's not perfect, but it does work. The next part is latest kernel vulnerability case studies. Last November, Apple fixed at least 2 GPU graphics driver-related vulnerabilities that I submitted. But I only got one CVE ID at the moment. The CVE ID is 2020-27914. The pattern of the vulnerability looks like this. The driver trusts the user mode input by mistake. The fatal thing is that this input is directly related to the number of kernel loops. Such code means heap of bound access. Here and here. So in summary, it seems that the root cause of this vulnerability is related to the lack of effective input validation. This type of vulnerability can be easily captured by kernel address sanitizer. And you will see why I used the words "it seems that." Next, let's look at the patch for this vulnerability. It's not complicated. The number of loops is limited to a fixed value before the loop starts. Everything looks fine, but let's think about it more carefully. These are 2 questions I leave to you. Number 1, is it possible for us to bypass the security update 2020-0007 and retrigger the vulnerability? Although the input buffer is on the kernel heap, is it possible to race against it? So this is a second question. The answer is yes. I have a demo for this case. Please allow me play the video. Yeah, today is the 5th of the January, and the latest version of macOS Big Sur is 11.2 beta, and build number is 20D5029F. And let me run my POC. Yeah, after a few seconds, we can see that the operating system has crashed. And because it's a 0 day, so I cannot leak too much information. But we can see here, it's a bad access and crashed. So on the left side of the target machine is my kernel debugger, this machine, which is connected by a debugging cable. And we can see the ARLDB is already outputting panic information. Okay. Here is a summary of the patch bypass. As the vulnerability has not been fixed, please forgive me for not disclosing the details of the vulnerability. But the TOCTTOU vulnerabilities, such as CVE 2020-27914, have been hidden in plain sight for a long time. And even after I submitted the vulnerabilities to Apple, they were not correctly identified by the kernel developers. This leads to the patch can be bypassed. Okay, the end. From the perspective of vulnerability research, I want to say CVE 2020-27914 remind us that we should re-examine the memory mapping mechanism of macOS and iOS kernel. And with this research as a new starting point, I believe we can do more. From the perspective of security engineering, I would say with the help of KMon project, I believe we can do better. Yeah, thank you. Thank you very much. Thank you for your time. Bye.